So, if the system is set into motion at time t0 by a displacement y0 units, and given an initial velocity v0, in other words, if we pull the spring down and then throw it upwards or pull it down further, we have initial conditions. Y at t0 is y0, the displacement, and y prime of t0 is the initial velocity that we give an impetus to this object. The whole problem is now a second-order linear initial value problem with constant coefficients. So it's an example of what's called free undamped motion. This motion will go on with no change unless something occurs to alter it. That's what it means by undamped. It keeps continuing to do whatever motion you let it do. So friction and air resistance do not come into play. If you look at the animation on the website, you can see the graph that shows position is a sine wave, and we can convert y equals c1 cosine of square root of k over mt plus c2 sine of square root of k over mt into a sine curve with fixed amplitude by using a trigonometric identity. And if we let a equal the square root of c1 squared plus c2 squared, and rewrite this as a times c1 over a times cosine of this plus c2 over a sine of this, right? Where a is this square root thing, as we said before. And now let theta be an angle whose sine is c1 over a and whose cosine is c2 over a. So we'd make this the sine and this the cosine of that angle. In other words, the arctangent of that angle, the theta is an angle whose tangent is sine over cosine, so c1 over a divided by c2 over a, which is just c1 over c2. And then we can write y equals a times sine of theta cosine square root of k over mt plus cosine of theta times cosine of square root of k over mt, and from the trig identity sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta, this is more simply written y equals a times the sine of k over mt plus theta, where our theta again is angle whose tangent is c1 over c2. So it's a sine curve with amplitude a equal to square root of c1 squared plus c2 squared, and period 2 pi times the square root of m over k. Remember how to calculate the period. Period is 2 pi over the frequency, so that would be 2 pi divided by the square root of k over m, which is 2 pi times the square root of m over k. And the phase shift would be negative square root of m over k times theta. To see this, we can compare the graph of y equals 3 cosine of 2x plus 4 sine of 2x, and y equals 5 times the sine of 2x plus arctangent of 3/4 plus 1. And I do that here in this picture. And it shows you, the reason why I put the plus 1 in there, so you could see one graph, one would be on top of the other. Otherwise, here I'll show you, I'll take out the plus 1, and you'll see that one graph is right on top of the other. So this graph and this graph are identical. This is usually a pre-calculus 2 problem I assign at some point to see that my students can manage to do that. But there it is with 1 added, so it's 1 unit above this one. So we do have this sine curve, which is precisely the equation of motion of this object.
Oh, I see.
Okay.